There we go. All right. So last time we talked about what? We talked about using those sort of general, sort of standard forms for our logic expressions. We talked about, things like and/or circuits, or and circuits, or and/or and circuits, how to define the levels, how to draw the tree diagrams, and all of that fun stuff. Are there any questions about any of that before we do this? Cool. All right. So, and the reason we do that is because that sets us up nicely to do what we're going to talk about today, which is convert those circuits to circuits consisting of NAND gates and NOR gates. And here's a couple sort of bullet point notes to make. First, in the real world, NAND gates and NOR gates are often faster, cheaper to build, and require fewer components than circuits of other gates. So, in the real world, NAND gates and NOR gates are often a lot faster. They click a lot faster, they operate a lot faster, they're cheaper to build, they require fewer components, fewer transistors, resistors, diodes, that sort of thing, to build than circuits of other gates, like AND gates or OR gates. So consequently, we will try to, we will convert our logic circuits to circuits consisting of only NAND gates or NOR gates. So we've got our process. We're starting to continue to develop our process, right? We started with truth tables or minterm, maxterm expansions, and now we have Boolean expressions. We optimize those using K-maps. We design our circuits in a standard form, like and or and, or multi-level versions of that. And then the last step, or the next step, not really the last step, is to flip that over and now convert them to either circuits of NAND gates or NOR gates, because if you do that, your circuits will be much, much more cost effective to manufacture. So that's kind of the last step, is to try to build everything out of NAND gates before you actually go to the presses. So let's talk about NAND gates and NOR gates sort of on a basic level real fast. We'll say that, here, let's talk about NAND gates first. And it's roughly defined as this. If f is a function of a, b, and c, a NAND gate is a and b and c inverted. Now, if we apply De Morgan's theorem to this expression, a and b and c, all of that complemented, what do we get? Yeah, absolutely, right? De Morgan's theorem says that we'll have a prime or b prime or c prime, right? This relationship will be very, very important to what we're going to try to do. Often, so you would sort of model a NAND gate as an AND gate, tied to an inverter to your output function f. Now, as a shorthand, because this is such a common thing to do, we'll define it as a NAND gate, similar to how we did the XNOR gate, right? Where we'll do an AND gate with our inputs, and then put a little bubble on the top to indicate that that output is being inverted. That's an AND gate. Any questions about it? All right. NOR gate's exactly the same thing. It's just for the OR operation. So we'll say that NOR, same deal. If we have f as a function of a, b, and c, well, that's going to be equal to a or b or c, all of that inverted. And by De Morgan's theorem there, we'll get a prime and b prime and c prime.
Going back to you can just shorthand it like that with including the inverter.
Yeah, so you just draw the bubble on the top. So drawing like this is the same thing as doing that. The AND gate with the inverter. Scoot that over a little bit. Okay. So if we're going to draw it, same deal. It's going to be just like our OR gate. 3 inputs, A, B, and C, into an inverter gets us F, and by shorthand we will draw the schematic symbol for a NOR gate as an OR gate with the bubble. A, B, and C, and that gets us F. Cool. Any questions about the general structure of NAND gates and NOR gates? Good. Okay. So when we want to convert a circuit, let's make a note here. To convert a circuit, of AND gates, or and OR, to a circuit of NAND gates or NOR gates, you apply the involution law. It's one of the ones we talked about. Does anyone remember which one it is? Involution law is the one that states that if we take x and invert it again, we get what we started with. So x inverted twice is just equal to x. It seems sort of obvious and not terribly useful, but as we'll see here, it's actually quite useful to make this conversion. So for example, let's look at first this Boolean expression, specifically this sum of products Boolean expression. So we'll say f is a function of a, b, c, and d, and it's equal to a or b, c prime, or b prime and c and d. Now let's go ahead and draw the logic circuit for this one directly. This is blue. We'll have 2 AND gates. First one takes its inputs as B, C prime. Second one takes 3 inputs, B prime, C, and D. And those feed into an OR gate with one last input, A. And that gets us F. So this is a 2-level AND OR circuit. Now we want to convert it to a circuit of NAND gates. And we'll do that by first taking our function F and inverting it twice. So F prime, prime. And from there we'll get this. We'll do a big bracket, then in parentheses A or B and C prime, or B prime and C and a D. All of that inverted, and then the whole thing inverted, right? So we've inverted it twice. Now we apply De Morgan's theorem just once, though, to that first inversion. And that's going to get us this. F is equal to, let's see, A or B and C prime, or B prime and C and D. All that prime is going to give us what? A prime and B and C prime, and B prime, C, and D prime. And all that primed again. Now hopefully from there we can see that this is in fact a NAND operation, because for all of these there's NAND gates, because we have B and C prime, so these guys are being ANDed, and then the result is being inverted. And these guys, B prime and C and D, are all being ANDed, and the result of that AND is being inverted. After that, all three of these terms, the A prime, the BC prime, and the B prime CD prime, all of that is being ANDed together, and again is being inverted. So we've got NAND gates at every level here. Everybody see that? So we're going to draw this circuit. Well, it's going to look like a lot like the circuit we started with. So we're going to replace everything with NAND gates. So we'll have a NAND gate that has B and C prime, and a NAND gate that has B prime, C, D, which will then feed a pretty sloppily drawn NAND gate. This is much better. Takes its input from the first two and A prime, and that result is still equal to F. And remember, it's still F because we took the inversion twice, which by the involution law says that we get to keep F. So if you stop and take a look at, I'm going to zoom out just a hair, and we look at both of these circuits, it's pretty simple to see what the formula is. You take all of the gates and you just swap them out for NAND gates. And the only input that changes, right, so B, C prime, B prime, C, D, all stay the same, right? The only one that changed was A on the output gate, got inverted and became A prime. And that's the process. So do you have a question?
I don't really know if there's an easy answer to this, but why is this better when it's still the same amount of inputs and gates?
Because for the scope that we're at in this class, there's really not a whole lot better. But the reality is, it only takes 2 transistors to build a NAND gate. It takes like 4 to build an AND gate. It takes like 6 to build an OR gate. So when you're starting to count, we're actually going to build the thing, right? When you physically put the thing on silicon, right? It's a hell of a lot cheaper to build NAND gates than it is to build AND gates and OR gates. So we convert it to NAND gates to make the final sort of production process a lot more cost effective. That's why. It's also a lot faster. NAND gates, again, because there are fewer transistors, are going to perform a lot faster. You can achieve much higher clock speeds with NAND gates than you can with AND gates and OR gates. Yeah?
Just a quick clarifying question. So why did it swap from an OR to an AND in the second one? Rather than like
From here to here?
No, see on the diagram, so it's like an OR going to the F, and then on here, is that the same? Yeah, with the input A, is that an AND gate?
Yeah. That's what I'm saying. They all convert to
so they
NAND
all,
gates.
is there a
Yeah.
reason why they all convert? Like in it, like
Because of the way De Morgan's theorem shakes out, right? Because right, all of these the OR operation that happens here under De Morgan's theorem becomes an AND operation because we inverted it twice. That external AND operation got inverted. So yeah,
Okay,
that
so
lets us
then it
convert
becomes
everything
an
to NAND gates. And yeah, and the reason why is it's faster and more cost effective.
Are we using the involution law at the second one? Is that why we didn't fully apply the Morgan's law? We came to B and C.
Right. So we're going to stop here, right? When we learned how to complement expressions, we went the whole way, right? We like flushed all the way out. But here, since our goal now is to actually implement these things and build them in a cost-effective way, we want to get NAND gates. We're going to intentionally stop here because we've got it in a place where every single gate is a NAND gate, and we've done it in a way that doesn't violate the truth table for F. Those are good questions. Any other questions? Okay, so let's quickly jot down the procedure, because you don't actually need to do the Boolean algebra in order to make this switch. So, well, let's do this. So I'm going to call this procedure designing a two-level NAND gate, or two-level NAND logic circuit. Okay. Step 1 is design a minimum or get. Let me change that to. Find the minimum sum of products Boolean expression. Oop. Step 2, from that sum of products Boolean expression, draw the two-level and or logic circuit. Then replace all the gates with NAND gates, of course. And step 4, the final step, is any single literals which are inputs to the output gate should be inverted. So, step 1, find the minimum sum of products Boolean expression, and it's important, it has to be the sum of products one, or else it doesn't work out, to get you NAND gates. Then draw the two-level and or circuit. Then replace all the gates with NAND gates. And then this last step, any single literals, which are inputs to the output gate, should be inverted. So if we go back and look at our two diagrams, it's exactly what we did here, right? We started with our two-level and or circuit. We replaced all of the gates with NAND gates. And then we left these literals the same, excuse me. And then we had a single literal, the A, that was an input to the output gate, that last OR gate, which became the input to the output NAND gate. That one gets inverted, but the rest of these guys stay the same. So that's the process. So now, first off, are there any questions about that process?
Would you still be a two-level?
What's that?
Isn't it still a two-level?
Yeah. So Joshua on Discord asks, what happens if you don't have a minimum sum of products when you try to convert NAND to NAND? Does the process break down, or is there just redundancy? It means you're not going to have the minimal solution, right? You want to start with the minimal sum of products solution because, I mean, again, getting that minimum sum of products is going to do like 90% of your heavy lifting, right? Then you want to convert to NAND gates to sort of, when we're converting to NAND gates, that's like the final step. I mean, that's when we're sort of like shaving off milliseconds and dollars, right? We're taking a little bit further, but you still want to get that optimal minimum sum of product solution because that's going to start you off in the best place. That's going to get you the minimum NAND gate circuit. Okay. So, to get a circuit of NOR-NOR, you're going to do exactly the same thing, except for a few changes. So we'll just make a note here and do an example. To get a circuit of NOR-NOR, the procedure is the same except that you start with a minimum product of sums and replace the gates with NOR-gates. So yeah, so you do a product of sums instead of sum of products, and you replace with NOR-gates. So let's take a look at an example of doing that. All right, let's say that we've got this. F is a function of A, B, and C, or A, B, C, and D, and is equal to now a product of sums expression, A or B or C, A or B prime or C, C prime or D, and let's say, let's do B prime, just for fun. B prime. Okay. So the first thing we'll do is draw our normal Boolean expression. Or actually, I take that back. Let's do the Boolean algebra part first, just to sort of illustrate that it works. And then we'll do the logic stuff. And in practice, you don't have to do the Boolean algebra. I just want to do it once, just to say that we did our due diligence and show that it works. So if I say F is equal to F prime prime, that means I'm going to get two big expressions here. All that stuff. A, B, or C, A or B prime or C, C prime or D, B prime, prime, prime. Now, what's going to happen there is by applying that first level of De Morgan's theorem, I'm going to get all of these expressions. So A or B or C prime or A or B prime or C prime or C prime or D prime, or we had B prime, now it's just B, and all of those statements are ORed together and then they're inverted. So again, we have a whole operation now that consists of all of these ORs that are inverted, that's a NOR, all of these ORs inverted, that's a NOR, all of these ORs inverted, that's a NOR, and then we have OR this, or that, or that, or that, all of that inverted. So that means our last gate is a NOR, just in the same way we had NAND gates before. So that's just to show that the math works out. So now if we draw our circuits, let's start with the original one with OR gates. So we have OR, put OR, what do we have? A, B, and C on the first one. A, B prime, and C on the second one. C prime or D on the third one. And all those go into an AND gate. Got ahead of myself. With B prime. That gets us F. Man, it's not a good drawing. To get our new NOR gate circuit, all we do first, remember, is convert all of the gates to NOR gates. All of the input, the original inputs all stay the same. A, B, C, A, B prime, C, C prime D. And that last one feeds them all and has B. And output F. So there we go. We took the gates, flip them over. All of the input literals stay the same except this last one, the output, which went from B prime to B. So that's how we draw a circuit of NOR. So any questions about how to do that process to convert a two-level circuit to NAND or to NOR? It's pretty straightforward. All right. The last thing we need to do today is then expand on that a little bit, because remember we had circuits that weren't just two-level circuits, right? We could have circuits that had multiple levels, and that's kind of what we want to look at last. Let's see. I'm actually going to lay out process one more time. So we're going to call it this, the process or procedure to design a minimum. Let's do this. NAND or NOR. I'm going to kind of draw them out by like differentiating between the two, but know that I'm talking, when I say NAND, when I write in pink, I'm talking about for the NAND gate circuit. When I write in green, I'm talking about for the NOR gate circuit, because the procedures are exactly the same. It's just the variables get swapped out. Design a minimum NAND NOR multi-level circuit. Step one is design a multi-level circuit composed of AND gates and OR gates with a OR gate or AND gate on the output. Right? So design a multi-level circuit composed of AND gates and OR gates with an OR gate on the output for making a NAND gate circuit, or an AND gate on the output for making a NOR gate circuit. Step two. Convert all gates to NAND gates and NOR gates. So do the flip, and then this is true for all of them. Single literals on odd numbered, or maybe they'll be a little more precise. Go away. Single literals which are inputs to odd leveled or odd numbered levels should be inverted. So, design a multi-level circuit composed of AND gates and OR gates, OR gates, AND gates on the output. Convert all gates to NAND gates, NOR gates, depending on what you're doing. And then three, no matter which they are, single literals that are on inputs to odd numbered levels, level 1, level 3, level 5, level 7, should be inverted. This is true of right, our circuits that we just did, even our two-level circuits, still follow that same procedure, right? This two-level circuit is still a circuit that has an OR gate on the output. We converted all the gates to NAND gates, and then this is level 1, right, which is an odd number of level. That input single literal got inverted, right? But this is level 2, which is an even numbered level, so these input literals stay the same. All right. So let's do a big monster of an example. All right, let's say that we've got our function f, which is this whole thing, a prime and b prime or c and d or e prime or f and g prime or h, I prime, j, or k, right? Whole lots of inputs. First, let's go ahead and do our tree diagram, just to get a sense of how this circuit is put together. Remembering that our levels have to be the same type of gates, right? So we can have a level of OR gates, we can have a level of AND gates, but we cannot have a level of AND gates and OR gates. So I've got some options to draw my starting level here, right? Because I have D or E prime, but I also have, which is not dependent on anything else, but I also have this H and I prime and J that is also not dependent on anything. All the other operations are dependent on other operations that came before it. Does it matter which one I start with?
It's probably more helpful to do the D and the D or E prime first, because then when you do like the ANDs with the F and G and the FI, you can do the C and that.
Yeah, you're absolutely right. So the short answer is it doesn't really depend, but there are reasons why you would want to do one or the other, right? So we're going to actually choose to do what she said, which is start with the D or E prime. And that's actually the only thing that can happen at that level, I think. So let's just go through the process here, if OneNote will cooperate with me. All right, so we did that. Now let's go ahead and we can do some AND operations. Well, we just did a level of OR, so actually let's make a note of that. We did OR. So the next thing that has to happen is an AND, because you can't really have a level, the levels have to alternate as well. So let's see, let's go ahead and do this. Let's do that. Fine, I'll leave that. And that. And then let's see what else can we do. We can do these guys. It's only during this class. Okay. So let's see. What else could we do?
Did you do H?
We could do HIJ now, although, and it wouldn't really make a difference. In fact, in the previous class we did do HIJ now. I'm going to wait until another level to go ahead and do that, right? You kind of don't want to do any levels that you don't have to right away. And this won't really affect the outcome. But yeah, that's a level of AND. Now we can do a big monster level of OR, right, which is going to have, let's see, those guys. Those guys, and this just won't let me win, will it? And those guys, and then let's see, but nothing else. That's a level of OR. Next up, let's go ahead and do a level of AND, and now we will do the HIJ. Start with that guy. I say please, maybe? Yeah, there we go. And that one. And then we're also going to have this HIJ line. Like that. And I just messed up. Like that, as our level of ands. And then finally, we'll wrap things up with our level of ors, which is going to be this whole expression, that expression, and then, well, let me do it this way. K is here, that guy's there, and then that whole expression over there. Finally, we're wrapped up with a level of ors. Man, it took a long time. Okay, so there's our basic tree diagram. Now remember, we go and count a couple of different things. The first one is the number of gates, which is all the places where stuff comes together. 1, 2, 3, 4, 5, 6, and 7. So we have 7 gates. The number of gate inputs is what we got: 2, 2, 3, 2, 2, 3, and 3. So I guess it's what? 2, 4, 6, 8, 10, 14, 15. Hold on. How many levels is that? 15, 16, 17. 17 gate inputs. And then finally, our levels, we had what? We had a level 1, a level 2, a level 3, a level 4, and a level 5. So we can say that the number of gate levels What's that?
The last one on the left.
Here?
Yeah.
It's 2.
Oh,
Unless it should be 3. Should it be 3?
yeah, it's 2.
Okay. Okay. So now let's go ahead and draw the logic circuit. I apologize, we're going to go like 2 minutes over time, but I'll try to go quick. Alright, so the first thing we had was, what, that OR gate that had D and E prime. Then we had some AND gates, which took first that one, and C, and F, and G prime. Then we had an OR gate, or a level of OR gates, which took those guys and B prime. Then we had a AND gate level, which took the output of the OR gate and A prime. And also here is where we did H I prime J. And then finally we wrap things up with an OR gate, which also took K. And there's our output F. All right. So there's our circuit of AND and OR gates. We've got 5 levels. Now, what type of circuit can we convert this to? Can we convert it to NAND gates or NOR gates? Why?
Just because the last one is an OR.
Exactly, right? All you do is look and see what the last gate is. If it's an OR gate, then you're going to convert to NAND gates. If it's an AND gate, then you're going to convert to NOR gates. So since that's an OR gate, we'll convert it to a circuit of NAND gates. And let's see. Let's do this. We're going to have Let's use a different color. First thing we do is just convert all the gates. Let's see. Just like that. And now if we remember, so we started with level 1, level 2, level 3, level 4, and level 5. So starting at the back end at level 5, 5 is an odd numbered level. So that means our inputs, D and E prime, since they are single literals, they will be converted to D prime and E. There we go. E. Now that NAND gate will feed into this guy, which has 2 inputs. And since this is level 4, which is an even numbered level, those will stay the same. Those will remain C, F, and G prime. And let's see, they feed into this NAND gate. Now this is level 3, which is an odd number level, so B prime becomes B. It feeds into this guy. And since this is level 2, it's an even numbered level, so these input literals will stay the same. A prime H, I prime J, and then they feed into this one. This is level 1. The output is always level 1, which is odd numbered, so that means K is going to become K prime, and our output will still remain F. And that's all there is to it, man. Cool? All right. There you go. If there are no other questions, comments, or concerns, yeah, remember exam 1 is live. Yeah, and that's all there is to it, man. I'll see you guys on Wednesday. Have a good couple days. And be safe. So, thank you. Yes, Aaron. You just decide, go to the very last gate, flip it over. And work your way back.